Question 6.10 says the thermite reaction involves aluminum and iron 3 oxide. The reaction is highly exothermic and the liquid iron is used to weld metals. Calculate the heat released per gram of aluminum reacted with iron 3 oxide. It gives us the heat of formation for iron, which is a liquid, because of course the heat of formation for iron when it's a solid is 0. To solve this question, we're going to use the formula for delta H of a reaction. Which is the delta H of the reaction is equal to the sum of the delta H of formation of the products minus the delta H of formation of the reactants, the sum of the delta H of formations of the reactants. Okay. And so we're going to have to look up some of these delta H's of formation. We're given the delta H of formation of iron. We need the delta H of formation for aluminum. And it's a solid, and of course that's 0 kilojoules per mole because aluminum is a solid at room temperature, and aluminum is the most stable state of aluminum. From appendix, so I get these from appendix 2, the delta H of formation of iron 3 oxide is negative 822.2 kilojoules per mole, and the delta H of formation for aluminum oxide is equal to negative 1669.8 kilojoules per mole, like that. And so we can plug those into our formula, and delta H of our reaction is going to be equal to negative 1,669.8 plus, we've got how many moles of aluminum? So we've got, how many moles of iron, liquid iron? We've got 2 times 12.40, and then we're going to subtract the sum of the heats of formation of our reactants. And for our aluminum, we have 2 times 0. And then for our iron 3 oxide, we have 1 mole of that. So, and that's negative 822.2 kilojoules. So let me just put, what I should do is do this, and then I'll put kilojoules per mole outside of the whole thing. And when you tally that up in your calculator, again, I'm using this formula right here, you end up with the delta H of your reaction is being negative 822.8 kilojoules for 1 mole. And it wants to know the heat released per gram of aluminum. Well, we know that we have 2 moles of aluminum in the reaction. So 2 moles of aluminum, and we know that in 1 mole of aluminum, if we go to the periodic table and look up its molar mass, it's 26.98 grams of aluminum. So my moles of aluminum cancel out, and I'm left over with negative 15.25 kilojoules per gram of aluminum, like that. All right. Oh, did I leave myself more space to solve it over here? Anyhow, the last section of chapter 6 deals with enthalpy of solution. If you've ever made a hot pack before, if you've ever, crushed up one of those hot packs where you make an aqueous solution and it generates heat, or maybe you've made a cold pack before where you make a solution and it is an endothermic reaction. Well, a hot pack would be something like when you make a solution of calcium chloride, because it tells us right here that when we make a solution of calcium chloride, we release heat. Whereas if we take something like ammonium nitrate and we make a solution of that, that absorbs heat, and so that would be a cold pack. That's how we'd make a cold pack. Now, this change in enthalpy of solution is the heat that's generated or absorbed when a certain amount of solute dissolves in a certain amount of solvent. And that change in enthalpy of solution is calculated as such. It's equal to U plus the change in enthalpy of hydration. U in this case is not energy, U is lattice energy. Lattice energy. And lattice energy is the amount of energy that's required to take ions in the solid phase and to put them, to put them as ions into, or to take an ionic compound and break apart its ions into the gaseous phase. So that would take a lot of energy. Yeah, it does. And that's why lattice energy is positive. Now, when you take those ions that are in the gaseous phase and you surround them by water or you hydrate them, that releases a lot of heat because they become stabilized by their interaction with water. And if you're still not following me and you need a picture, because a picture is worth 1,000 words, here's the process that describes the enthalpy of solution for sodium chloride. And we saw on the previous slide that the enthalpy of solution for sodium chloride is 4.0 kilojoules per mole. And where does that come from? Well, remember that delta H of solution is equal to lattice energy plus the delta H of hydration. And remember that lattice energy is when we take the solid ions and we convert them from sodium chloride solid and we break them apart into their ions in the gaseous phase. And that takes a lot of energy. In fact, it takes 788 kilojoules per mole. And you can imagine, well, those ions in the gaseous phase, that can't be very stable. But when I surround them with water molecules, the water molecules can interact with both the cations and the anions to stabilize their positive and negative charges, respectively. And so we take these ions in the gaseous phase and we convert them to sodium plus aqueous and chloride minus aqueous, and that stabilizes them. And that's why the delta H for hydration is a negative number. You can see it's negative 784. So overall, when you tally those up, you get the heat of solution. And again, I told you what the heat of solution was on the previous slide. It's the heat generated or absorbed when a certain amount of solute dissolves in a certain amount of solvent. So we take that solid ionic compound and we put it in water, we get the ions that are hydrated. And since enthalpy is a state function, it doesn't matter how we get to those ions. Okay, there's no way to measure the heat of solution directly, but we can measure the lattice energy and we can measure the heat of hydration. And when we tally those together, we get the heat of solution.